computer. All right, we should be recording. I haven't done this in a minute, so there we go. All right, so we are moving on to the next topic that we cover, and this is on the types of matter, how matter behaves, the properties of matter. All of those things are going to be covered in this unit. So, types of matter, unit 2. All right, so what is matter? Well, matter is anything that has mass and volume. I think sometimes we get used to saying anything that has mass and takes up space. Takes up space and volume mean the same thing. But volume is the preferred word choice here. So matter is anything that has mass and volume. Some things that aren't matter are like the light in this room. Light is pure energy. It's not matter. It does not have mass and it doesn't take up space. Imagine if light were made of matter, though. Like every time you turn the lights on, it would be like heavier because it would have mass and it would take up space. Like if it was really bright, you might not have room to stand. You'd have to squish. I'm just saying. It could be weird. But light is an energy source, heat's an energy source, all of those things. So those don't have mass and they don't have volume. They don't take up any space. All matter is going to be divided into one of two categories. Everything in the universe is going to go in one of two categories. Everything. If it's matter, it's going into one of these two spots. And we're going to talk about those. These substances are pure substances or mixtures. So everything in the universe that is considered to be matter, so it has mass and volume, is either going to go in the pure substance category or it's going to go in the mixtures category. Everything. All right, so we're going to talk about these individually, with the first one being pure substances. There are two types, there's two categories of pure substances. There are elements, which is anything we can find on that periodic table over there. So lithium, element. Gold, element. Chlorine, element. Elements, if we look at a sample, there would only be one type of atom. So if we had a sample of something and we were to be able to look at it on the atomic level, if every atom that was in my sample is all magnesium, then this is the element magnesium. It's a pure substance. Again, anything you can find on your periodic table, and there's one on the wall there. There's, and probably give you one maybe in the next week or so. I don't think you'll need it for this. Compounds are also pure substances. These are two or more elements that have been chemically combined to create a new substance. So sodium is an element and chlorine is an element. But if I chemically combine sodium and chlorine, I get sodium chloride, which is salt, which has very different properties. It's something completely different and new from what the parts of it are. All right, so pure substances, elements and compounds. Either way, it's going to be something you can find on that periodic table or something that's combined from those periodic table. I tell another way, and I know it's not a foolproof method, but it works a lot. If it sounds sciencey, it's probably it's probably a pure substance. Like if I were like sodium hypochlorite, doesn't that sound sciencey? It is. That's a pure substance. It's a mixture. That's not 100% true, but it works a lot. Oh, sorry. Let me go back. Let me try to figure out how to go back. Okay. And I thought I had already clicked on that. Compounds have to be chemically separated. We chemically combine them to form something new. It has to go through a chemical process in order to separate as well. All right, so pure substances, that's a lot of things. But more often than not, we are going to run into the other type of matter, which is a mixture. Mixtures have a defining quality of that you can separate these by physical means. And we haven't talked about physical and chemical yet, but you've talked about it in your previous education. But that just means that I can separate it without changing the identities of what it is. Like I can filter coffee out of water and it's still coffee, and then it would be, you know, there's still water. I can go through this process and not alter the identities of what I'm working with. There are two types of mixtures. There are homogeneous mixtures or homogeneous. Those are both correct pronunciations of that word. Either way you say it, it is correct. Homogeneous or homogeneous. And this simply means that if we examine our sample, every part of it is the same as every other part of it. There's no variation. The composition is fixed. It's the same. The second type are heterogeneous mixtures. And they're the opposite of homogeneous. Homogeneous means the same. Heterogeneous means different throughout the sample. All right, so homogeneous means the same throughout, heterogeneous means different. And again, this is not 100% foolproof, but it works for me and it might work for you. I always just think if I had a big bucket of this in front of me, whatever sample it is I'm looking at, and I were getting spoonfuls of the sample out of the bucket, if every spoonful is exactly the same as all the other spoonfuls, I'm working homogeneous. If every spoonful is different, even slightly different or a whole lot different, I'm working heterogeneous. I don't know. That has always worked for me. Maybe that will be helpful to you as well. I just think about it. If I had this big part of it and I was taking little pieces, if they're all the same, homogeneous. If they're different, heterogeneous. Homogeneous mixtures are also called solutions. These have very small particles. The particles in the solution are less than 1 nanometer or billionth of a meter in size. So very, very small. All solutions are composed of 2 parts. The first is the solute. That's what you are dissolving. The part that is dissolved. And the other part is the solvent. That's the thing that does the dissolving. So solute is what you dissolve. The solvent is what you dissolve it in. For example, salt water. That's a real easy one, and it's one that comes up on a lot of like the practice worksheets and things that I've seen. Salt water. Salt is the solute because that's what you dissolve, and the solvent is water because that's what you're dissolving it in. Water is actually what we call a universal solvent. Almost every example that includes water, water will be the solvent. Most things dissolve in water. Solutions, though, can be, they don't have to just be liquid. The air can be a solution, and it is a solution, especially when we're talking about humidity. Here in the South, we got a lot of that. You know, it's the temperature is 80, but the heat index is 126. I mean, that's how this works. In that case, water would not be the solvent, though. The air would be the solvent, and the water would be the solute. So, like I said, but most of the time, it's pretty straightforward. What you dissolve is the solute, what you dissolve it in, solvent, and that's usually water. Not always, but most of the time. So homogeneous mixtures are also called solutions. Heterogeneous mixtures. There are actually two types of heterogeneous mixtures: colloids and suspensions. All right. The first of these are colloids. Colloids have particles that we consider intermediate in size. They're kind of like in the middle. They're not small enough to be solute particles and part of a solution. So they're kind of in the middle when we talk about particle size. So we just means they're too large to be considered a solute in a solution, but they're also too small to kind of settle out and come out of the thing that they're suspended in. One of the major identifying factors of a colloid is that it will exhibit what we call the Tyndall effect. And so this is, anytime you see Tyndall effect, your brain needs to connect that to colloids. In the Tyndall effect, we see light being reflected by these particles. The best example I can think of is fog. If you are driving and it's very, very foggy, what the advice is to lower your headlights, put them on low beam. And the reason you're doing that is to reduce the Tyndall effect. You are trying to reflect less light. If you put your bright beam or your high beams, your brights on, then you end up actually having less visibility. Fog is a colloid. The particles are not small enough to just be part of the humidity, but they're not large enough to fall to the ground as precipitation. So they're just stuck there in the air, and you may not know they exist until light interacts with them. So this is a really, really good example of the Tyndall effect, and it's something we've all familiar with. So fog. There is a subset of colloids called emulsions, and all emulsions are colloids, and we're going to talk about some examples of emulsions. So they still have these odd-sized particles as part of them. We're not really going to see the Tyndall effect there because these are going to be more solidified. But basically an emulsion and is there anything that comes out of a can and foams up. So like hair mousse or shaving cream or that weird canned cheese stuff, whipped cream in a can, anything that comes out of a pressurized can and expands in size. Those are all emulsions. And emulsions are colloids. So when you see examples like shaving cream or spray cheese, if those come up, you're going to make sure to classify those as a heterogeneous mixture that is also a colloid. All right. The other type of heterogeneous mixture. Sorry. Oh, I forgot. I put some more examples on this one. Some more examples of colloids are milk, mayonnaise, jellies, paint, blood. Blood is generally colloidal. Has different size particles suspended throughout the different types of blood cells. Sorry, I forgot I added that sentence. This is an example. There's nothing to write down here, but on the left side, we have a liquid here that would be a solution. And on the right side, we have a liquid, and probably in the light, you couldn't tell the difference between the two of these. But when we use a flashlight, a beam of light, and shine it through, we see that we have this Tyndall effect being shown. So that is giving us our colloid right here. So solution on the left, colloid on the right. All right, our final type of heterogeneous mixture are suspensions. Suspensions have very large particles. They are generally over 1,000 nanometers in size. The particles in a suspension will settle out. They'll fall to the bottom, okay, unless it is stirred or agitated. So the defining characteristic of a suspension is the fact that the particles will settle to the bottom unless it is agitated, shaken, stirred, moved around in some way. The best example I can think of, because it's one of my favorite things, is orange juice with pulp. I actually buy the orange juice carton that says lots of pulp on the top of it. But what's the first thing I have to do when I get that carton out of the refrigerator? I got to shake it, because all that delicious pulpy goodness has settled to the bottom of the container. So I have to shake it up to get it resuspended. I like to feel like I'm actually drinking an orange. Apparently, I am in the minority of people. Most people like pulp-free. Yeah. It's enough for me. There are other examples. Say if I took some pond water up here and I had a big jar of it and I shook it up and left it on my desk, and I came back after I left it over the weekend. We came back in. Where would you expect to find the dirt in that at the bottom? So that would be an example of a suspension. It's going to settle to the bottom. And when it does that, that's how we know it's a suspension. Here's an example. I don't even know what this is. I think it's sand and water. I think that's what I saw. But you can see here, this has been shaken up really good on the right side. And then on the left side, you can see that it's settled out to the bottom. So any questions about the types of matter? That's it. That's all there is. Well, let me go ahead and turn our Zoom off.